Okay, in AQA Aqua Ions for A-level chemistry, you need to know that ions, so metal ions, when they're surrounded by 6 water ligands, and that's whether they are 2 plus or 3 plus, you need to know that these act as weak acids. Now, for some people watching this video, you're in one of my classes and we've done this already, so it's just a little recap. So we need to say why they're weak acids. Well, weak acids release H plus ions into solution and they partially ionize. So we need to be able to see why they partially ionize. So again, I'm going to go really quickly on this. If you've got a metal ion surrounded by water ligands, so I go H2O all the way around here, this is the equation that you would write to show why they are weak acids. So notice that I show a couple of the bonds here on one of the water ligands. Okay, so this is 2 plus or 3 plus. Let's just actually go with 2 plus. One of these hydrogen ions can drop off into solution. So this hydrogen ion can come loose, so to speak. So you'll notice, therefore, that you will make metal with 1, 2, 3, 4, 5 waters, and now one of the waters become OH. So to draw that as an equation, you could write M, 2, 3, 4, 5. This is now an OH. This is an H2O. 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 Sorry about the big fat pen here blocking, not being very clear. But then the H plus ion drops into solution. Hence, metal ions are acidic. So here's a little bottle here. I've got copper sulfate. Copper sulfate is an acid because copper sulfate contains copper surrounded by water ligands. But inside this bottle now, most of the complexes, the copper complexes, look like this, but some of them look like this. All right, not many, probably about 1 in 15,000 look like this, hence weak acid. All right, you could be asked to write the equation. You might want to draw it like this, but more often than not, you would draw it like this. Metal, H2O 6 times. Actually, I'm going to go with copper, for example, Cu, H2O 6 times. 2 plus, write an equation to show how it acts as an acid. You go Cu, H2O 5, OH, square brackets around there. 2 plus goes to 1 plus, H plus like that. So, metal aqua ions are acidic. This is important from where we're going with this. All right, the reason for this, you have a metal ion in the middle. There is a coordinate bond to the water ligand. What this metal ion does, firstly, it draws electron density towards itself. Okay, so there are electrons in each of these bonds and they're being drawn in that direction, pulled towards the metal ion. All right, what this does is it weakens the bonds, and in particular it weakens the bonds in the ligands. So number 2, this weakens the OH bonds in the water ligands. And number 3, H plus ions break off into solution. Okay, so all of these other ligands, they all have their OH bonds weakened a little bit, but what we tend to find is in one of the water ligands, an H plus drops off into solution, so you end up with 6 waters and one of them's an OH. They're a weak acid. All right, what you can also be asked, so that's the answer to why are they acidic. The metal ion, the positive metal ion draws electron density towards itself. This weakens the OH bonds in water ligands. H plus ions break off into solution. You could also be asked why 3 plus, notice now that's 3 plus, why 3 plus is more acidic. Well, if you think about it, if this is a 3 plus, it is now the metal ion, the 3 plus, is now more charge dense because it's a 3 plus. If it's more charge dense, it's going to draw more electron density towards itself. It's going to weaken the OH bonds in water more, meaning more than a 2 plus, therefore more H plus ions break off into solution. So on this sheet now, in dark black, you have an answer to why are metal aqua ions acidic. And then in pencil written over the top, we now know why a 3 plus is more acidic than a 2 plus. So remember that metal 3 plus is more acidic than metal 2 plus. All right, for these reasons, take a little screenshot, write that down. That's your revision card to answer that question. We're now going to look at a range of chemical tests that show how metal 3+ are more acidic than metal 2+. We can use these chemical tests to identify ions and things like that. You need to know these chemical tests and you need to know the colours, and that's probably why you've clicked on this video, because you need to know the colours of aqua ions. Alright then, so the way that I teach this is I draw a table. Alright, now this table, you need to know at A-level chemistry, you need to know about copper, you need to know about iron 2+, you need to know iron 3+, and you need to know about aluminium. So if I'm writing this out from scratch, I go Cu, Fe, Fe, Al, Cu, Fe, Fe, Al. The reason I do this, 2+ iron, 2+ iron, 3+ iron, the ions are next to each other, the 2+ and the 3+, and aluminium down the bottom. And now I'm going fast, but you can always pause this video. So from what we've just said, the 2+ aqua ions are at the top, the least acidic, and here are the most acidic. Aluminium is the most acidic. It is 3+, and it's smaller than Fe, so it's the most charge dense. So we've got least acidic all the way down to most acidic down here. Each of these boxes, even though I've just written it as copper 2+, iron 2+, iron 3+, please remember that this is copper H2O 6 times 2+, and so on. This is Fe H2O 6 times 2+, Fe H2O 6 times 3+, aluminium H2O 6 times 3+. So these are the aqua ions. So we write Cu, Fe, Fe, Al. There you go, there's the copper solution there. I've got some of that. I've got some aluminium solution here. We'll do the colours later on. I've got some iron 2+ here, and I've got some iron 3+ here. Alright, so what we need to know, because these are acids, this topic is all about, we're going to now react them all with bases. So we're going to react them firstly with OH-, then we're going to see what they do with excess OH-, then we're going to see what they do with ammonia, which is a slightly weaker base than OH-, then we're going to react them with excess ammonia, and then we're going to react them with carbonate. Alright, so at the minute it looks like you've got tons and tons of things to learn. However, shortcut. Using this diagram, writing the diagram as Cu, Fe, Fe, Al, you realise that only aluminium 3+ will react with excess OH-, and only copper 2+ will react with excess NH3 from Cu, Fe, Fe, Al. Alright, what I'm going to do now, I'm going to put that sheet to one side. We're going to come back to it in a minute. We're going to talk about how these things react with OH- and how they react with NH3. So, let's go. If you've got a metal ion like this, copper 2+, actually I'm going to get rid of the 2+ because I'm going to draw it like a complex. We're going to go H2O, 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 and then these ones over here I'm going to leave with all of the bonds shown. This is 2+. Now, we know from the start of this video that this is acidic, which what that means is these H+ are a bit loose. Don't say the word loose in an exam, but these are ready to drop off into solution. We know that actually they drop off on their own. Well, if we add a base to this, if we put some OH-, which we know is pretty strong base, OH- is excellent at picking up H+. So what happens when we add OH-, an OH- will do this. It will pluck off an H+ by forming a coordinate bond, and that will break this bond, and you will make, if you see this, you will make H2O, H2O, and that will become an OH on the complex. The same thing will happen here. And for a 2+ ion, that's where it stops. 2 of the water ligands become OH-. So you end up with this, Cu, bum, 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 bum. This is now an OH, this is now an OH, water, 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 water. Can't be bothered drawing them on because I'm running out of space. This OH- and this OH- both become waters, so you make 2 H2Os. Alright, this happens for all of those species on our Cu, Fe, Fe, Al. So copper, Cu, H2O 6 times 2+, becomes Cu, H2O 4 times OH twice. Alright, if it's a 2+, you get 2 OHs there, and you make 2 H2Os because there were two OH minuses that became water. These OH minuses have become these H2Os. All right. So finish that off, neaten it up a little bit. Now this thing here, you'll notice that the complex you've formed, this one, has now got no charge. Because it has no charge, it doesn't dissolve in water. So let me say that again. Because it has no charge, it doesn't dissolve in water. That means it forms a precipitate. All right? So that precipitate, really quickly, let me just show you. There's some copper. Here's some hydroxide. Have I got any hydroxide? Sodium hydroxide? Oh, you fool. I'm in my chemistry lab at the minute, so... yeah, sodium hydroxide. So what I'm saying is, I'm going to take this, I'm going to add some hydroxide. We should see a blue precipitate form. And you can see there, hopefully, we've got this lumpy blue jelly forming inside there. I don't know how clear that is on the camera. Right. So, let's go back to our table. How this looks on the table is this. We know that when we add two OH minuses to here, we will make Cu, H2O, 4 OH, 2. That's not quite fitting in the box there, I need a slightly sharper pen. And the OH minuses become H2Os. So, in this case, the iron would do exactly the same. Because it's iron 2 plus, you will make Fe, H2O 4, OH2, and you'll make H2Os as a byproduct. In here, you will make Fe, H2O, and it's different, it's 3 plus, so that happens 3 times. 3 waters are affected, and they become 3 hydroxides. Fe, H2O3, OH3, and you'll make 3 waters. And aluminium will do the same. Al, H2O, 3, OH3, and you'll make 3 waters. All right, each of these in here is a solid precipitate. You've seen that copper makes a blue precipitate. What have I got here? Iron 2 plus. Oh, what have I got? I'll take a little bit of iron 2 plus and some sodium hydroxide. Here you get a green precipitate. Happens like that, really nice. Have I got any aluminium? Yeah, I've got some aluminium. Aluminium makes a white precipitate. I'm going to run out of time on my phone here, that's why I'm going so quick. Is it going to go white? Oh, it disappeared again. That's the trick about aluminium, I'll tell you that in a minute. It goes white. I ruined that a little bit, didn't I? For those who know what's happening. Alright, I'm going to add a little bit. Watch that writing underneath. Okay, it goes a little bit blurry. A white precipitate forms. Don't know if you can pick that up on the camera. Not very concentrated solution. There you go. There you go. White precipitate is formed. And iron 3 plus, a brown precipitate formed. So hopefully you've seen all this in class with your teachers. Let's add this. Brown precipitate. Boom. Brown precipitate forms. Let's move them out of the way. So what we've got in this column are precipitates of the hydroxides. Copper plus hydroxide makes copper hydroxide. But this is an acid-base reaction. This base on the top plucks hydrogens off the complex. Remember that. This base here plucks hydrogens off the complex because these hydrogens are a bit loose. With a 3 plus, it does the same thing, but eventually you will end up making the precipitate of the complex that has no charge. Alright, so far we've got this, and we've realised that 2 plus do it twice, 3 plus do it 3 times. Aluminium. Now from the very start of the video we said that the more charge dense metal ion you are, the more acidic you will be. Now aluminium is really much more acidic than the rest. So what it tends to do, instead of just having, because it's 3 plus, instead of just having 3 hydrogens removed, it can actually go even further. And it can go further on to eventually you end up with all of the hydrogens being moved off the water ligands. Now if you remove all of the hydrogens off the water ligands, you will end up with this complex, AlOH6 3 minus. I'll try and show you that really quickly. So aluminium, boom, 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 boom. OH, H, O, H, H, O, H, H, O, H, H, O, H, H and then O, H and then H. There's aluminium H2O 6 times, and all of that's 3 plus. So what normally happens is an OH minus comes and plucks off that one, an OH minus comes and plucks off that one, an OH minus comes and plucks off that one, and you end up with your white precipitate. Let's look at the diagram. This, you end up with this. Now normally, as we can see on the table, that's the end of the road for metal 3 plus. But aluminium, this 3 plus ion in the middle, is so good at pulling electron density towards itself that actually if you just add a bit more OH minus, you can remove another H plus, you can actually remove another H plus, and you can remove another H plus, and you end up with this. Just about see it, aluminium with an OH, 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 and an OH. That is aluminium with 6 OHs, and overall it will be 3 minus, because you've removed 6 H pluses from a 3 plus complex. So just remember, this box is at AlOH6 3 minus. I'm going to try and slow down a little bit. I've only got 9 minutes left of memory on my phone. That's what I'm battling against here. When it is charged, when a complex is charged, it will dissolve. So everything in this column will be a solution. These are all chargeless. They are neutral. All of these will be precipitates. I'm just going to write PPT. And everything in this column, well, it's just this one, is charged again, so this will be a solution. So, focus just for a sec. If you've got aluminium here, colourless solution. What I'm saying here is if you add sodium hydroxide, it will give you a white precipitate. Oh, maybe that wasn't the aluminium. Dope. You'll get a white precipitate. There we go, there's the white precipitate coming there. It's gone cloudy. If you keep adding it, ooh, goes white, 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 white. Please go colourless again. Nearly, it's gone whiter on it. Need a bit more space in my beaker and a bit more sodium hydroxide. So I'm very firmly in that column at the minute. Okay, still white. Can I add a bit more? God, it's going whiter, isn't it? Need more sodium hydroxide. Need more sodium hydroxide. There you go, definitely going white. Oh, starting to clear. There you go, it's going clear. See, chemistry does work. It's gone clear again. I've now got that. Nearly ran out of space in my beaker. So you add a bit of hydroxide, you end up with this neutral. When it's neutral, it will be a precipitate. We know it's no longer a precipitate. We know it's no longer neutral, sorry. When it goes colourless again, that's this. So we go from colourless to precipitate and back to colourless. Some of you will have done that at GCSE, I'm sure. Making a right old mess here, aren't I? Okay. So far it looks like we've got tons to learn. Now here's the neat little thing about this table. NH3 here is a base just like OH minuses. So if you remember this diagram from before, when we added hydroxide, we're now going to do the same thing. There's my copper with 6 waters. If we add ammonia, ammonia is also a base. It's not quite as strong as hydroxide, but it'll just do the same thing. Look, so look what we did last time. OH minuses plucking off H's. Ammonia does the same thing. It plucks off these, hang on, loose H pluses. Ammonia plucks off the loose H pluses. All right, so that means you're going to make exactly the same product. Look, you're going to make this. Copper with 4 waters and 2 OH minuses. You're going to make the same precipitate that you made before. But instead of making H2O, maybe you can work out what you're going to make. Well, you're going to make an NH3 that has picked up an H+. So you're going to make 2 NH4 pluses. So then, in this column, what I want you to realise is, yes, you made Cu H2O4 OH2 with hydroxide. You're going to make the same chemical, Cu H2O4 OH2. But in this case, the byproduct will be NH4+. In this one, you're going to make Fe H2O4 brackets OH2, and you're going to make some NH4+. And this one, you're going to make Fe H2O3 OH3 with the byproduct of NH4+, And in the bottom one down here, you're going to make aluminium, H2O, 3, OH3, and some NH4+. Notice, ammonia is not a strong enough base to make aluminium lose any more hydrogens. So aluminium, where aluminium will react with excess OH-, it will not react with excess NH3. All right. The only thing that happens with excess ammonia is copper. When you add excess ammonia to it, so I'm going to show you this. What my diagram is telling me is if I take copper that looks like this, copper solution, and I add ammonia, so I've got some ammonia solution here, I will expect a blue precipitate, same blue precipitate as before. There we go, there is a blue precipitate in there. But if you keep adding it, eventually you get this beautiful deep blue solution. One of my fave colours that, I don't know if it's picking it up on my camera. Alright, because what happens if you add excess ammonia to copper is you make this complex, Cu, NH3 4 times, H2O twice, and it's a solution. It's because it's got a charge. It is this complex. I know I've gone over into the next box, but this is ligand exchange. This is not acid-base reaction. This is the only box on the whole of this that is to do with ligands exchanging. You put enough ammonia in, and ammonia actually just takes the place of the water. So if you can imagine this diagram, you've got copper in the middle, surrounded by 4 ammonias and 2 waters, overall with a 2+ charge. Okay, so I'm just going to get another coloured pen. Darn it, I haven't got another coloured pen. I've got a green over here. Just walking around my lab. Right, I've got some nice colours here. Time's a ticking. Got a green, got a red. Okay, so what have we learned so far? Alright, because time's about to go, and then I haven't done carbonates yet. I'll do them on a separate video in a sec. Right then, this column and this column are exactly the same. You just need to know what these columns do, and look at them. It's easy. If it's a 2+, you form H2O4 OH2. If it's a 3+, you form H2O3 OH3. They're precipitates. They're precipitates. You need to know the colours of these precipitates. Blue, because they're the same. Green, because they're the same. Brown precipitate, brown, because they're the same. White, because they're the same, and it's not a transition metal, so it's not colourful. You also need to know what goes on in this box. This box is special. Aluminium is the most acidic, so it can lose more H+s. It's a solution. It's a colourless solution because it's not a transition metal. And you need to know what goes on in this box. And they say in AQA this is deep blue solution. Deep blue solution. All right. Because I've got limited storage on my phone, I'm 23 minutes in. We're going to stop there. I'm going to come back in a sec with another video. You need to be able to write equations for what happens when this turns into this. So you go copper Cu H2O 6 times 2+ plus 2OH- will make this plus 2H2O. You get a mark for saying it gives a blue precipitate from a blue solution. Let me just remind you of these, sorry. That's a blue solution. This is a green solution. All of these are green. Just say green. Don't say sage green or anything like that. Green, 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 green. This is orange, and this is colourless. All right. Yes, so you could be asked for what happens when you add excess ammonia to copper 2+ solution. Well, you're going to make a deep blue solution. You need to know the formula. You need to be able to write an equation. I'll show them in a separate video. So this shows you basically the simplicity, and it's not laid out like this in your textbooks, unfortunately. You add ammonia, you add hydroxide, you get the same results with Cu-Fe-Fe-Al. But you add excess ammonia and excess hydroxide, you need to know these special things happen. We'll come to carbonates in the next vid. I'm just repeating myself here, but I'm going to redraw this video, this table for you, and start the next video shortly. This is going to take a while to process though. Okay, thank you, bye.